Hello, everyone, and welcome. This is our first webinar of 2019, and today we will be talking about the latest and greatest features in our HydroComp PropCad Premium Edition package. This webinar will start with just a very quick overview of HydroComp PropCad and also the additional utilities in the Premium Edition. We'll keep that really short. And then we're going to jump right into our newest feature, the Import CAD File utility. And we'll do a quick overview of the utility, what it does, what its use cases are, the input file requirements, the utility process, and also the output from the utility. The idea of this utility is to speed up or to decrease the time it takes to pull in a propeller design into the PropCAD environment. A lot of times, we can start within PropCAD and build up our design, but if we have an existing design that we're trying to get in there, the process in the past has been to use Scan Converter, and it's been a bit slow and manual. So we'll see some drastic improvements today on importing existing designs. After we run through the use cases and the process, we'll actually do a demonstration of the import utility live, just so you can see how much of a speed improvement it is, how fast it is, and how capable the utility is right now. And then we'll have a few conclusions. We'll take questions. I'm happy to answer any questions online here if that's something you're comfortable with. And I'll put my email up on the screen at the end. You are always welcome to contact me by email to discuss things that might be sensitive in private. All right, let's get started here. For those who may be unfamiliar with PropCAD's role in the design space, PropCAD is focused on the geometric design of marine propellers. So it's all about the blade shape and the integration of the sections into a blade form. There are no performance calculations in PropCAD. There are some strength calculations, but its primary purpose is to produce 2D drawings, 3D CAD models, and documentation such as offsets reports, classification, thickness calculations, inspection reports for building propellers. Within PropCAD, we have an integrated builder that allows us to build kind of standard designs, such as the B series, the GON, Kaplan style propellers, and there's a few others such as surface piercing wedge style, thruster styles, and a few other distributions that are included in the builder. The builder allows you to build up a propeller very quickly and easily, and this is all included in the standard edition of PropCAD. A few years ago, we released the PropCAD Premium Edition, and this Premium Edition is a set of tools that goes above and beyond the standard tasks that would be done with PropCAD. It's really geared towards manufacturers, people who are not just responsible for the propeller design, but are responsible for quality, manufacture, and documentation. So there's a lot of tools that go beyond just doing a design. The first one here is Scan Converter, and this tool has existed in some form within our software for many years. The original idea was to take data from scanning devices, inspection devices, basically coordinates off of the face of the blade, and we would enter those coordinates into the software. That would allow us to develop the section shapes and derive kind of the design data. The Import CAD file is kind of an updated version of Scan Converter that pulls the data automatically from a 3D CAD model instead of manually entering things from that. So you'll see some similarities if you've used Scan Converter in the past. The other big piece of PropCAD Premium is our pattern corrections utility. So for manufacturers who must take a design and actually account for the surface material that needs to be milled away or ground away, and also the shrinkage of the material that they're casting in. This allows them to actually take a design, describe their shrinkage rates and the mill stock, and create an enlarged pattern, or a larger geometry that can be used as a pattern for production, so that by the time they cast that, they have enough material. When the casting shrinks, there'll still be enough material to grind and mill and have your final design within that envelope. If there's any questions about that, I'm happy to discuss that further offline. But today we'll really be focusing on this this newest feature, this Import CAD file. The real goal of this is to automate that extraction. Previously, again, we would use an inspection device and pull points off, maybe manually enter them in. It's very much a time-consuming process. So we can take something that used to take several hours, and using some automation by kind of pulling this data out of a 3D model instead of manually pulling it off of something, we can really quicken this up from a few hours down to a few minutes. And we'll see that live in the demonstration. It will really be very quick. The requirements for this process are that you have, of course, the premium edition that gives you access to the utility. It is available in the last few releases of 2018. However, this is really a 2019 feature. We've been kind of operating in a development and beta mode, and it's really ready for production now. So the next requirement that you need is a CAD file or some sort of capture of the 3D geometry. This is becoming increasingly easy. We'll see a slide on this next. Once you've captured that propeller geometry in the computer in a 3D CAD format, we may need to reduce that model down to a single blade. So if you had a 3-blade propeller and you scanned all the blades, you just have to chop off 2 of those blades so that we're only inspecting 1 blade. And generally, you'll choose the best blade, the one that's in the most pristine condition to be pulled into PropCAD. The last requirement is an ASCII formatted STL file. And this is a fairly common format. Almost any CAD program can output an STL file, and that was why we started with this file type. In the future, we'll expand to more as it makes sense, but for now, this is really able to accomplish what most people need. 3D capture of the propeller geometry. This is an important aspect. This is not something that we personally do, but you'll find that it's becoming easier and easier to find this as a service, to be able to send out your propeller to someone who specializes in either ferro technology or white light scanning or something like that. And they'll quickly scan the propeller. The scans are very high quality. You can see things like stamps on these scans. You can see scratches. You can see flecks of paint and rust and cavitation burns and all that stuff. So it's really a very mature technology, and it's becoming increasingly affordable and accessible. And that's why now, instead of pulling from a pitchometer, it's becoming easier and easier to actually get a full 3D model. The issue with these 3D models that PropCAD is addressing is that you do a scan of the propeller and it's very much static. And when you scan it, you get all the bumps and bruises, the damage, the dings that are present on that blade. And if you're trying to create a derivative design or create a variant in another pitch, it's not easy to manipulate something that has 10 million points from a 3D laser scan. So this is kind of the process that we feel this utility is really going to help. It's going to allow people to extract data from these scans into a more usable format, and they'll be able to later manipulate the data. So once we have captured our propeller design, you can see this one here was captured in a fairly nice format. The next thing to do is to remove the blades that we don't need or the sections of the hub that we may not need. One thing I did not mention here that is important is to register the bore of the propeller through the origin, so that this should be basically centered and laying flat in the CAD space. Once you've oriented your blade and removed the things that aren't important, we need to save this in a STL format. And there's one thing to be aware of when you save files into STL. This will tessellate your files, as in it will break the surfaces up into triangles. You need to be careful when you break that up into triangles. You need to have enough triangles that you keep the full definition of the blade. Propellers being very curved surfaces, these can get quite dense on the edges. They can get quite dense in general. So it's important to kind of review your STL output to make sure it's an accurate representation of your original data capture. The next step, once we've prepped that file as an STL, ASCII STL format, we can bring it into our utility. There's a button on the bottom down here. We hit import and we'll be prompted to select the file. The file gets pulled in, it gets placed into 3D space, and at this point we need to actually orient it so that the shaft axis is along this red axis here. This is the X positive direction. There's a little notation here, you'll see a bit later, it says shaft forward, and in this particular case I had to rotate the model 180 degrees to get that direction. But once that's in there, we're more or less ready to pull data from it. The next step here is to define our section cuts. That's that next button in the step sections here. There are some preset distributions as far as the density of the sections. So typically our blades are rounded near the tip, so we want to have a few extra sections up here. That's why you'll see a 9.9, 9.875, 9.75, 9.5, etc. The other thing that we want to do is make sure that we bring our sections close to the hub. So you may have to add a section in towards the hub in order to kind of capture the data as close to the hub as possible. The last few things to do are to set the user diameter. This is kind of in case it's very difficult to capture the tip, you can inset this in slightly. We have to describe the rotation direction so that we know what pitch this should be, more or less. And we have to describe the style of the edges. So if we have an airfoil shape like a B-series propeller, we probably have closed edges, so we'd select those to be closed. But if we had a surface piercing style propeller, a wedge style with a really thick trailing edge, kind of like this trailing edge right here on the bottom right, then what we would select would be an open trailing edge style. And by selecting open, that just tells us that we're going to delete a few of those segments there, that it's not connected. You'll see a little bit of this coming up here. Once we've defined this distribution here and we are happy with the preview, we can press the build button. The build button is going to quickly intersect each one of those radii. It's going to pull out the section offsets in 3D cylindrical space, and then it's going to show you basically the derived data. So we're looking right here at the derived 2D section shape. Here is the pitch, the core, the thickness, the skew, the rake. We can also go through here and adjust the pitch plane. For instance, if we had a lot of camber or we had some cup in the blade, the cup would kind of come down here, and we would want to make sure that that cup is not included in our design pitch. So there are some ways you can adjust that pitch plane, and the feedback here of your actual pitch, that can be helpful to make sure that things are smooth, especially with there's cup propellers. I'll show you that it's a little bit easier to see in the live demo when we can zoom in on this section shape and select different vertices and things like that. Once you're all okay with how the data is coming in, how the pitch planes look, and your derived data, you can just hit OK, and this data immediately comes into the PropCad environment. And once it's in PropCad, it's a lot like any other project that you've worked with in the past. You can quickly go in, you can change diameter, you can change the pitch, you can add rake or subtract rake from a propeller. There's a lot of things you can do very easily with just a few clicks of a button. So changing blades, diameter, pitch, rake angle, those are all single numbers that you change, and the blade is scaled up or down to those parameters. Again, you can go through and review sections to smooth things, to get rid of those bumps and bruises that were included on the original 3D laser scan, but you may not want in your final design. So that makes it basically, by the time you've gotten your laser scan process through this import utility and into PropCAD, you're really able to refine the design in a way that you weren't before with just a plain Faro scan or something like that. You know, using that 3D geometry, there's no easy way to manipulate it. But once we've derived parameters in PropCAD, manipulating parameters is a lot easier than manipulating points in 3D space. And that's the power of this utility, hopefully. So now what I'd like to do is shut down this PowerPoint for a few minutes and start running through a live example. It just should take a few minutes here, and hopefully it goes smoothly. So I'm going to pull PropCAD up. This is the 2018 version of PropCAD. We'll be releasing the 2019 version shortly with a few updates, but this utility is available in 2018 currently. We keep the utility right here. This is where the scan converter utilities are. And at the bottom, you'll see the new Import CAD File utility. We click this. It's going to ask us if we are okay with overwriting our data. We're going to hit no, and yeah, of course we're okay with overwriting the data. And I'll make this full screen so that we can get a good visual. The first thing to do is to select our units. We want the propeller to be in inches, so this all looks okay. And we also need to select the units of our file that we're about to import, which is also in inches. The next step here, you'll see once we've pressed units, the import button has become illuminated. We can select import, and we can go and grab our file. As soon as we hit open, we see the file is being imported in here in percent, and we'll get a preview right away. So this looks pretty nice, pretty dense. The edges are nicely defined, and so there shouldn't be any issues here. We can see that we have a finite trailing edge, so we may want to leave that as an open. What we have to do is we have to rotate this propeller 180 degrees so that the forward direction is this way. Right now we're facing the wrong way. Anytime you click on an axis, you'll be shown a small arrow head showing the rotation. So if we go to the Z-axis here, we can see that, okay, we want to rotate this 180 degrees. There we go. We're in the right location now. There are a few other things we could do. For instance, we could shift this propeller back an inch or so to get it better aligned with the design GL there. So there are a few ways that you can kind of quickly go through and reorient the propeller as needed. The next step here, this is right-hand rotation, so that's okay. The leading edge is a round leading edge. The trailing edge we'll just select as closed as well, because we'll just pull the data in. It'll be okay. But if you had a very wide trailing edge, like a surface piercing blade, that's when you'd select this open option. The next thing to do is to select our section distribution. The default distribution really isn't dense enough. There are some presets here, so we could come down and select just this round tip distribution, or perhaps something a little more dense, and then we can come in and customize it. For instance, we can put one really close to the tip, and down here, I'm not sure if the 30 is going to go low enough. We may have to add a 25, and sure enough, actually it looks like we can probably get away with a 20% radius, so let's go in there and add that 20% in as well. We just click the plus button, tell it we want a 20% radius, it goes in. Okay, great. And that's close enough to the hub for me. For this demo, I think it will be just fine. And okay. Let's see how it does. And in some cases, if you do have a hole or something in the file, you can have some issues. In this case, everything came in perfectly. So again, very, very quick. We have all derived our initial set of design data here for our what is nominally a 1.0 radius all the way down to our 20. If we click any of these columns, we can see the pitch distribution here. So this looks pretty good, but there's some interesting stuff going on at the tip where the pitch is really high. We'll check that out in a minute or so. If we look at chord is nice and smooth. That's always good to see. Thickness, perfectly linear is what we would expect. Here's the skew and the rake distribution. So one thing we had mentioned earlier was setting pitch planes. So you can see down here, we have our section shape. We can zoom in and take a look. Now, I would actually probably want this nose point or the pitch plane to be based off of kind of a face-based pitch plane instead of a nose tail. So if I wanted to change the pitch plane, I can grab a point, say right here. I can click that point and I can just say set this as my nose point. It shifts it up. And what you'll also see is that the pitch for this section changed just slightly. You can look again at the tail. The tail's already all set. So this is a representative pitch plane for this plane. And we could go through and repeat this process for each section. I can go here and set this as the nose. Set this as the nose. And you'll see it's just adjusting the pitch plane slightly. We can see these adjustments kind of changing the data here. The nose. And I'm just trying to get it a little closer to what the actual spec of the design is. The other thing that we had seen earlier is the tip here. So there's some interesting stuff happening here. Let's take a closer look. And again, the reason why this pitch is so high is because this pitch plane is really not accurate. All we have to do is come in here and set this nose point. The face and back get re-derived, and now our pitch is coming in much closer. The rest of these, nose point. And so I think we're pretty good through here, at least through the 70. Now this step is really optional. This is just something I wanted to point out. We're going to probably use this video for user education in the future, and this is something that people should know about. It's not a critical step unless you're really trying to match data. If you're just trying to pull a design in, you may not have to worry about this. And we're almost done here. And in this case, where we're getting a little bit of a belly, I may actually want to set a nose and a tail pitch plane. Tail. Nose. Okay, great. One more here. Set the tail. And let's just take a look at our data here. So what I can see when I look at this is, okay, this 50%, maybe it needs an adjustment. It looks like the pitch isn't very smooth, so we go to 50, and sure enough, I forgot to set this tail point. Clicking back. Now the pitch is so much more smoother. This is really good. So I'm happy with this at this point. I'm looking at my distributions. They're all very smooth. I could play with this area a little more, but we're really talking about 1/3 of an inch pitch difference. It's not a big deal to me. So I'm just going to hit OK and continue on. As soon as I hit OK, all these offsets are going to be brought into PropCAD. By default, this is going to show up with 4 blades. But again, we can reduce the blades down to 3, which was the original design. Now, the issue here with the speed is because that there are about 150 to 200 points that we extracted per section. So PropCAD's going through, rebuilding these with splines, making sure everything is smooth. It's building our 3D model. It's also building our 2D drawing. So here we can see our blades have come in very nicely. Let's go take a look at the 2D drawing. One thing I'm going to do is I'm going to shut off a few of these closely entered sections. The rest of it should be okay. I'll turn off the title block. We don't need that. Great. These sections look great. Our data's in. Let's take a look at now manipulating this data. Let's say that we wanted to change the pitch. So it's currently a 20 by 28. We can easily add a few inches of pitch to this, maybe make it a 20 by 32. When we change the pitch, it's going to ask us, do you want to scale the existing distribution? Of course, yes. We hit OK. And what we should see is this blade should get a little bit narrower as we increase the pitch. And of course, it's a little bit slow to rebuild this. I'll show you another trick right after this that we can do to speed this up. All right, 3D data should be a little narrower now. So the reason why this is a bit slow to rebuild the propeller, let's take a look at how many points we have in each section. So you can see it's extremely dense. The 70 has 156 offsets on the back and 153 offsets on the front. One way to reduce this data is to use distribution files. So we can export a distribution file. I just go in here and I say example section. I just want this section file here. Hit OK. Successfully exported. And what it did is it just took all this data and packaged it into a file. The file can be a lot quicker than the entered version because it doesn't have to rederive things like thickness and chord length. Okay, let me fix that. Doesn't like that the tip is at 0.99 instead of 1.0, but that's an easy fix. And okay. Ooh. So much for that. That was quick. Sorry about that. I guess I broke something. Let's see if I can pull that file up again. Luckily, I have it saved. All right, back in action here. This one just happens to have a hub. But what we should be able to do is just select that file there and import that in. Now I'm not going to try that again. We'll just kind of continue on here as if this was already reduced. But from here, it's very quick to be able to go and change things like number of blades. We can make it a 5 blade. We can take some rake out of it. We could increase our diameter, 22, 32, and let's just see what happens to our design. So very quick to take that data and then be able to kind of manipulate it into different shapes, to smooth things, to get a better look at things, and then automatically prepare your drawings and your 3D files as needed. 2D drawing, 3D file here, quick to export. So hopefully that gives you a quick overview of the capabilities of that tool and the process. What we saw was pulling in the STL file, setting up those pitch planes, deriving our data, and bringing it into PropCAD, where we could then manipulate it and prepare drawings and 3D models as needed. There's also, of course, reports that we can prepare that can document our derived parameters. They can also document the 2D offsets. Here's the pitch, thickness, chords, and the following pages will be the offsets in 3D space as well as 2D space. And with that, I'm going to switch back to the PowerPoint. And I think the only thing we have left is to do some questions. So we think this is a major improvement on the process that we had with Scan Converter. For customers who have used Scan Converter in the past, you know that it's very manual. There's a lot of copy and pasting of data or manually entering data, and it can take hours to get a single design into PropCAD. Now with this STL utility, if you have access to laser scanning, you can get a 3D model really quickly, and it's very easy to pull that data in just a few minutes. From there, it's quick. It's easy to manipulate that data within the PropCAD environment in ways that you couldn't with a typical scan. So that's the conclusion here, and hopefully you guys are as excited about this as we are. You know, we think this is going to allow people to bring their design data in, and when they couldn't necessarily do that before in a quick way, and make it a little bit more accessible to people who just maybe aren't quite as computer savvy to go through and enter in tables of offsets. This is just another way that gives you a little bit more interface and a little bit more control and automates that process a bit more. Now with that, I'd like to take any questions. Again, you can use the chat here to ask questions, or you can also email me if you'd like, or give us a call. Our phone number here is 603-868-3344. I'm happy to discuss this with any of you guys further, but hopefully it's something that's valuable to you guys coming up. And I'm just watching the attendee chat here, so if anyone has questions, you can leave them in the chat. Well, while we're waiting for questions, I just want to say thank you to everyone, and I'm going to end the recording here for people who are rewatching this. Thank you for your time and attention, but we'll continue here with the questions. Do you have an STL file size that you recommend? I have been using STL files between 50 and 80 megabytes generally. There's kind of a twofold issue with the size of the file. So you want to have a dense enough file that it very accurately represents the scanned geometry. But as you get a denser and denser file, that means more points are pulled into PropCAD. And so at some point, you do have to reduce the points in a section to something a little bit more manageable, especially if you want to smooth things out. So my recommendation is I'd probably use something between 50 and 80 megabytes. That's a pretty large reduction from what typical 3D scan files are. It's something that we'll be kind of working with our customers on in the future to see if we can improve, one, being able to pull very large scan files in, but then being able to intelligently reduce the point count in those files to something that's easy to manipulate. Thanks for that question. That was a really good question. Is there a function to smooth out bumps and hollows to get a new theoretical section shape? There are. There are some tools in here. Let me see if I can just open something that. Oh, that other one was fine. Give me 1 second here. When we get data, I don't have an example that would show kind of this smoothing process, but for instance, let me just kind of take something and throw it out of whack, and then we can talk about smoothing. If you have something like, this, where, and I'll make the model kind of unsmooth as well. If you have an issue where you have something that's not quite smooth, and we can't really see it here in this model, but if we look at this chord length, you might see that some of the derived data is not smooth. One thing we can do is there are some tools here to fit individual pieces of data. So, for instance, we can fit this one cell. We'll get a small preview of the change in the data, and we can hit OK here to accept that fit. So that's one way to kind of smooth out things that you might find. For instance, if you find a bump in the thickness or a bump in the chord or some skew that doesn't look quite right. The other thing is you can smooth entire columns. So if we derived a column that was not quite smooth, we could kind of get the overall effect of all that data by using some of these smoothing tools here. So you can see that there's a variety of ways to kind of fit everything back. Now that is all about smoothing parameters. When you get into smoothing section shapes, generally what my process is there is data that is derived. I will print out a drawing of that data, and then I will try to recreate a smooth version of that section using the builder. And this is something that I do commercially for our customers. They'll say, I want to pull this design into PropCAD, but I do want something that's smooth, and I want to be able to go through and manipulate the thickness of the edges or the cup or the camber. And so we'll take a section shape that's pulled out of the extraction, we'll review it, and we'll find the best settings to go in and make a smooth, truly parametric, editable version of that section shape. So that's generally what I recommend. Now, of course, you can also go through at any time. You can manipulate these offsets. You can change the position of these offsets and fit them and smooth them as well. So if you have a section shape that's just a little bit ugly, has a bump in it, you can go through and actually refine it from the 2D offsets if you like as well. Hopefully that answers your question, Wayne. The next question, can PropCAD export 3D model to directly use it for CFD simulation without preliminary preparing in CAD software? That's a good question. I would say there's when going from PropCAD to CFD, there is probably some intermediate steps in between. We do not have kind of an STL export from PropCAD. What we export out are IGES files, or we export out macros native to specific CAD programs. So for instance, if you're using SolidWorks, I'd recommend exporting the SolidWorks macro. What that does is it rebuilds your geometry natively using SolidWorks loft and surface commands and all those good things, so that your geometry is built up natively in the CAD program, so you don't have any troubles when you go to CAD CAM or CFD. Now, if you're looking to go from PropCAD directly to CFD, right now the closest thing you can do is export an IGES file and then bring that IGES file into some sort of meshing software and discretize it into a mesh for CFD. But most people want to take the model and add fillets, do their details on the hub. So generally there's some intermediate step that involves doing some final work in CAD in order to get the final CFD model. Hopefully that answers your question there. When you have face camber, what is the best practice for aligning the nose and tail? Yeah, when we have sections with camber, it's a bit difficult. Um, for me, I have a good feel for that, so let's just put some camber in so everyone will understand what we're talking about here. This is about selecting a pitch plane for a section that has face camber in it, as in it doesn't have a flat face that. Oh, sorry, hold on. Turn something off real quick. We can see just the regular section shape. All right, sorry. The screen wasn't big enough for me to reach the option down here in this table. Um, we want to see. Yeah, I gotta turn off the points so you guys can see this. Polyline. Okay. Decrease this down here, and hopefully we can see this all now. But when you have face camber, obviously we don't have that flat piece that we can just go and select a nose and tail. And if you have some curvature in the nose, it can be difficult as well. In that regard, it's the same thing with cup on the trailing edge. You have this cup surface that kind of comes down here, and maybe I'll add cup just so we can really, see what we're dealing with here. 1/4 inch and 1.8. We add cup to the section because this really makes it a little bit more obvious. I go to a lower section. All right, you just have to add way more cup. So what we're looking at right now is kind of a proper pitch plane. What you can see here on the trailing edge is that, if you selected this last point as your pitch plane, it's going to push this up and it's going to get a different pitch. So one strategy I would suggest is have a rough idea of what the blade pitch is going into it. That way, when you're reviewing the pitch curve, you can set that pitch plane and kind of look back and say, is that pitch curve smooth? Is that what I would expect? That would be my recommendation. But some of it comes just from kind of experience, and if you can look at the blade and know a rough idea of what the cup drop is, well, then you're going to kind of want to go and set your pitch plane until your trailing edge point comes down to what you expect for cup drop. So, here we're at almost an inch of cup. This is a very large propeller. But that's kind of how I would suggest adjusting your pitch plane. Kind of have a rough idea of what the pitch should be, maybe what the cup should be, and you can set it up that way. Now, another way to do it is just to put the pitch through the nose and put the pitch through the tail. And if you're not concerned with the derived pitch parameter in PropCAD, the geometry in 3D is still going to be the same regardless of the pitch plane. So you really only have to set these pitch planes when you need to prepare a drawing or you need to extract accurate design data. If you're just trying to pull in a blade and increase the pitch 10%, okay, just pull it in, let the pitch plane be whatever it is, scale the pitch by 10%, and you're done. Okay, next question. Can it export distributions of blade geometry? Absolutely, we can export any of these distributions. So if you've gone through and you have a project and you are particularly happy with the skew distribution, for instance, what we can do is we can do File, Export, and we can select PropCAD distributions here. So when we go to save this, we'll be prompted with which distributions do we want to use. Earlier, we tried to set up the section file. We had a little bit of a glitch, but this does work really well in general. So I can say, okay, I'm going to export my SKU file, and it goes out there. Now, when if I look at this file here, hopefully we can see it. Here it is, SKU file, send to edit pad. What we can see is this is just a text file, and the data has been sent into this distribution file. Now, if we want to go and use that definition, it's very easy. We come in, we select import, and we pick that SKU file. And then we can actually scale the distribution as needed. So it kind of saves that distribution shape. It also allows us to rescale it up or down as we need. Is there a way to compare different files and scan imports? Say you have 2 to 3 scans of the same design that have small differences. How would you compare those? We have to do this a lot. There's not an automated feature for comparing them. I use a couple different things. First of all, I'll overlay the scans in CAD without PropCAD at all. Just overlay them in CAD so I can see, visually see some differences in 3D space. The other way to do it with PropCAD is to import your scans and to compare them on a drawing basis and a derived parameter basis. So if you import 1, 2, 3 scans and they're all slightly different, they should in theory have slightly different parameters that get derived. And so you could go to the reports or the drawing in order to kind of see those parameters. And you could compare, okay, the pitch of the 70 here is 28, but in this other scan, it's 29. And that way you kind of have an objective way to compare those scans. The third way I'd recommend is to actually take drawings and you can overlay the drawings on top of each other using the DXF export or using a projector table with some light behind it and taking 2 printouts and laying them on top of each other. And you can manually check how well the outline matches, how well the section shape matches, etc. Which export formats are supported in general? IGES is great, thank you. Okay, yeah, there is general purpose formats such as IGES, and then there are specific formats for most CAD/CAM packages, CATIA, Rhino, SolidWorks, PowerShape, Delcam, Mastercam. The list goes on and on. If you have just email me if you have a particular software that you're using. I'll let you know the easiest way to export and import that data into your CAD software. All right, these were really good questions, guys. I appreciate your input and your questions. Good feedback for me. How would you make the correct sizing when you want to make castings from your design? Okay, yeah, great. This is a different topic, but it fits well with this webinar because this is about PropCAD Premium, and our Premium edition has a pattern corrections utility in it that we previously touched on here. So once you've imported your design and you're happy with it, you've smoothed it out, what we can do is we can generate a pattern. Now, a pattern is an oversized version of the design file. And what I'll do is I'm going to pull up this pattern correction utility. Here it is. Don't mind this for a second, but I'm going to quickly pull up the help file just to give you a quick understanding of what this is and how this works. So patterns here. What we have is our design file here, and we need to create an oversized pattern. Now, that oversized pattern has to account for the material that we remove from the surface the stock material here for grinding or CNC milling, it also has to account for the shrinkage of whatever material we're casting in. So this is called pattern shrink or pattern maker shrink. You can see that right down here. So what we'll do is we will just do a quick example here. I'm going to make this full screen. What we're looking at is our propeller design in the background, and what's overlaid on top of it is the pattern design. So they're exactly the same right now because we have not corrected anything. But the first thing I will do here is, now the first thing I'm going to do is make this propeller a lot smaller because it's 500 inches. It's just way too big for me to understand. So I'm going to make this 50 inches, which is something I understand. Let me just do that really quick, and we'll go back into the patterns. That way I can apply what I understand to be appropriate shrinkage and stock offsets. All right, pattern corrections. Okay, it comes in here. So for instance, if we added 100 thousandths of material that we could remove from the face and 100 thousandths of material we could remove from the back, and also 100 thousandths of material from the edges here. So I'm just going to do that really quickly, and let's see what happens to our pattern. We hit calculate, and what you'll see is these surfaces, this wireframe is now offset from our design surface, just on the blades, just where we defined it. And let's take a look at the tip here. You can see as well, this continues all the way around the outline of the blade. So everything, the outline, the face, the back, etc., have all been expanded. There are similar corrections you can do on the hub. You can add 120 thousandths to the hub, hit calculate, and you'll see that this mesh will offset here on the hub as well. There it is. But that would be great for preparing a model that we could use as a CNC starting point. But we also want to make some considerations for the shrinkage of the bronze as it goes from molten metal bronze into solidified bronze. So typically, you see 2.5 to 3.5%. I'll use 3.5% here as my pattern making shrink to so that we can actually see some changes here. So I'll just do a diameter shrinkage factor. Typically, we would see all these numbers filled in here. But what we should see when this calculates is that it's expanded the diameter here by 3.5%. We can look, okay, that's great, that looks good. Now, similarly, we probably want to expand the thickness by 3.5%. So 1.035, we hit calculate, and it's going to expand the thickness by 3.5%. So this is a really useful tool. It can quickly kind of correct your design. But the best part about this is this information is saved into your file. So if you do your first casting and it's close, but it maybe needs a little bit less grind stock, or it needs a little bit more, it needs maybe a little bit more scaling of the pitch, for instance, then you can come in a second time and you can say, okay, this is what I did before. I want to actually go through and I want to scale pitch as well in order to get that. The reason why these are all these options are individual is that during the development of this utility, we talked with a lot of casting companies. Every foundry has a slightly different implementation of their corrective factors, and so we just allowed them to correct it on an individual basis. For instance, some manufacturers will correct diameter and pitch, but they won't scale up skew or chord lengths or anything like that. So it just depends on your process and your understanding, but all the options are there as you need. All right. Hopefully that answers any questions about this pattern making utility and making compensation. This is just another way to visualize the same thing. Again, offset surfaces instead of a wireframe, it's yellow. But what this allows you to see is where your original design kind of penetrates your pattern. And that's kind of an indicator that you're going to have some rubbing in the mold as things contract. You may have some distortion. So this is a very useful utility, a very useful view. When you hit OK here, it's just going to pull all this data back into PropCAD so that you could, again, smooth it or manipulate it, export it to SolidWorks, prepare a 2D drawing for your casting. It turns into basically a regular PropCAD project. Great. I hope that answered your question. If you have any other questions on pattern corrections, casting, things like that, I'd be more than happy to discuss that with you offline over email. Are there any other questions that I can answer for you guys? Hello? Well, I'm not sure. I think my screen share just kind of unexpectedly ended. But if this is I think this is probably a good point to stop at. If there are, we went through exactly an hour, so perfect time to end. If there are any questions, please contact me by email. Give me a call here at the office and ask for Adam. I'm happy to talk with you on the phone. And I think that there's some really good potential here to get people up and running really quickly with PropCAD. So if this is of interest, let's talk further offline, and happy to answer any other questions you guys have. Again, thank you very much, all of you, for your time today. It's always really nice to have a nice group of people who are interested in what we're talking about, and I love sharing with you guys. So anytime I can reach out to you, let me know. Thank you very much, and have a great afternoon. Bye, everyone.